request for it to be a 30-minute talk with 30 minutes for discussion, so I'll kind of skip through certain parts fast so that there's a bit more time for discussion rather than just to talk. This work actually goes back a long way to work I did with Todd Thompson starting 20 years ago, and has sort of been an ongoing interest of mine, which has been rejuvenated in the past few years. And I should say, if you have questions as I go, I'm not sure how you normally handle this, but feel free to ask them. I don't easily see the chat right now, so maybe if there are questions, you can either just ask or raise your hand, and Morgan can call on you. So thanks. Okay. Also, I'll stress the other person that a lot of the work that I've been doing is with is Philip Kemsky, who's a graduate student at UC Berkeley finishing this year. So just to make sure we're all on the same page, by cosmic rays, I mean a non-thermal population of mostly relativistic particles that are basically everywhere in the universe where we can look. So in the solar system, galaxies, the intra-cluster medium of galaxy clusters, presumably the circumgalactic medium of galaxy halos, the intergalactic medium, etc. And why I find them particularly interesting is they sort of satisfy what you might call the holy trinity of research questions. There's a lot of extremely interesting and subtle physics, in particular plasma physics, and a lot of nuclear physics goes more into understanding the observational constraints in the Milky Way. Cosmic rays are measured in the interstellar medium of the Milky Way to be an energetically important component of the galaxy, and energy density similar to that in turbulent motions, for instance. Likewise, probably not quite as large in energy density, but nonetheless significant in galaxy clusters. And so they have a number of potential implications for understanding structure formation. And then lastly, they're observable. Cosmic rays dominate the emission we see from galaxies at a variety of wavelengths, in particular in the radio, non-thermal emission, by synchrotron emission from electrons, and in the gamma rays, pion decay, gamma ray emission. So just to orient you, the kind of classic measurements that are made from in situ detection of cosmic rays, or to measure the flux of cosmic rays hitting a detector that might be a balloon initially, or on the space station, or in a satellite. The Voyager has actually now measured cosmic rays outside the influence of the solar magnetic field, which is very important for understanding lower energy cosmic rays. So it's really clarified the low energy spectrum of cosmic rays. The higher energy spectrum of cosmic rays is measured because those particles penetrate into the solar system without being strongly affected by the solar magnetic field. And there's some kind of in-between energies where we still actually don't know super well the spectrum because of the influence of the solar magnetic field. But if one integrates up the flux as a function of energy, most of the energy is in GeV protons. Cosmic rays are detected, sort of many things in the periodic table. A large fraction of the periodic table shows up as cosmic rays, as well as things like positrons, antiprotons, etc. But for the purposes of the stuff that I'm going to talk about, where we're interested in the dynamical effect of cosmic rays, that's mostly the GeV protons that matter, because that's most of the energy. Those particles have a Larmor radius, which is a little bit bigger than the size of the sun. They have a Coulomb mean free path, which is a lot bigger than the size of the universe. And so how cosmic rays travel through the interstellar medium and the circumgalactic medium, et cetera, is governed entirely by the magnetic field, in particular by small scale fluctuations in the magnetic field, which alter the propagation of cosmic rays. So just to give you a feel for the possible energetic importance of cosmic rays, this is a very crude estimate of the energy in cosmic rays in dark matter halos of different masses, galaxy clusters, Milky Way mass galaxies, dwarf galaxies, different mass dark matter halos. And the calculation here is simple. We basically assume that 10% of the energy of all supernovae goes into cosmic rays, and about 10 to the minus 3 of the energy of the rest mass energy of supermassive black holes also goes into cosmic rays via jets. That 10 to the minus 3 number might actually be relatively conservative. Could be higher than that. And then what's plotted here is the ratio of the energy in cosmic rays in these different systems to the thermal energy of a virialized halo of gas. So take the baryon fraction of the halo at the virial temperature of that halo, that is a thermal energy, and compare the energy in cosmic rays to that. And so what you see is that in particular around Milky Way mass halos, that energy in cosmic rays from supernovae is very significant, comparable to the virial energy of the virialized halo. It goes down at low masses and high masses, and this just traces the stellar mass function of galaxies, which is comparatively, galaxy formation is comparatively inefficient at low and high masses. And so for those who are used to these plots, this is basically like the M star and halo relation, just in different units. For black holes, you'll see that their effect is biggest in higher mass halos, primarily because that's where we have the best information on the kind of black hole mass function. But the cosmic rays from black holes might well be more important, and probably are more important, than the cosmic rays from star formation in higher mass systems. So given this rough energetics, there's basically, I would say, 3 lines of arguments about the importance of cosmic rays. One is that in kind of Milky Way and lower mass systems, they may be an important source of galactic winds. In higher mass systems, cosmic rays may be an important way that feedback energy from supermassive black holes is coupled to the surrounding hot halo, which can suppress star formation and keep massive halos quiescent, basically elliptical galaxy formation. And then I would say one of the new insights that's come out of the work that we've been doing is that actually the most dramatic effect of cosmic rays could be on the circumgalactic medium of Milky Way mass halos in this sweet spot of this diagram around 10 to the 12 solar mass halos. And I'll talk a little bit about that. Okay. So the big uncertainty, and why I think this is such an interesting physics problem, is that this plot here is a total energy. But to really understand the effects of cosmic rays, you need to know where that energy ends up, right? You need to know whether all that energy in cosmic rays generated by supernovae ends up staying in the galaxy, in which case the energy density relative to the energy density in the galaxy would actually be quite a bit larger than implied by this plot. Or do the cosmic rays just happily stream out of the virial radius of the halo, travel out into the intergalactic medium, in which case in this estimate, we're overestimating the importance of cosmic rays because in fact their energy is spread out over a larger volume. So the big uncertainty then in understanding the effects of cosmic rays in galaxy formation is really the propagation problem of where do the cosmic rays actually end up. So what do we know about that? We know a decent amount about that empirically in the Milky Way. The kind of classic measurements, which go back decades, are that we can measure that some cosmic rays are produced primarily by what are called spallation reactions, basically nuclear reactions. A high energy proton hits a low energy proton in the interstellar medium and produces boron or beryllium. That's the dominant production channel for boron and beryllium in cosmic rays. And so you can measure, we know the cross section for that reaction. You can measure the optical depth of that reaction by measuring the ratio of boron to other cosmic rays like carbon or oxygen. And so since we know the cross section and you measure the optical depth, you can measure the average column density of stuff that boron and beryllium have moved through. And then in one case, in particular in radioactive beryllium-10, you actually have an absolute lifetime measurement because you know the radioactive lifetime of the beryllium-10 cosmic rays that are produced. And the basic result that comes out of that is that cosmic rays leave galaxies, or our galaxy, on a time scale of about 30 million years for GeV cosmic ray protons. It's lower at higher energies, but for the GeV protons that are energetically the most important, it's about 30 million years. And that time scale is, of course, really short compared to the Hubble time or even the dynamical time of the galaxy, but it's very long compared to the light crossing time. The inequality here is backwards. The 20 million years is long compared to the light crossing time of the galaxy. And that means that cosmic rays don't leave directly. And if we interpret what they're doing as undergoing a random walk, a diffusive process, the mean free path that's inferred is a few parsecs at a GeV, just that time scale and a volume that's about the size of the radius of the galactic disk, or a diffusion coefficient of about 3 times 10 to the 29 centimeters squared per second. And on scales larger than that mean free path, just like basically we can treat gas in galaxies on scales larger than the mean free path as a fluid, we can do the same thing for cosmic rays. They're a relativistic fluid with this diffusion coefficient. The challenge theoretically in understanding the impact of cosmic rays in galaxy formation is that we don't understand very well where this 30 million year number comes from. And thus we don't understand very well how to extrapolate it to other galaxies. So we think that the scattering of cosmic rays, the mean free path of cosmic rays, is set by small scale fluctuations in the magnetic field, fluctuations that are resonant with the cosmic rays, meaning that the waves that scatter the particles are waves that have wavelengths comparable to the Larmor radius of the cosmic rays. So these are waves that have wavelengths comparable to the size of the Earth's orbit around the sun, roughly, tens of solar radii, hundreds of solar radii for GeV particles. And the amplitude of the fluctuations that matter are something like delta B over B of 10 to the minus 3. So to predict this from first principles is daunting. That's certainly not possible in any computer simulations of galaxy formation, right? You want to know what is happening to the magnetic field on solar system spatial scales, right? That's an extremely difficult thing to do from first principles. There are basically two theories for where those waves come from. One is that they come from the small scales of a turbulent cascade. The interstellar medium is turbulent, the magnetic field is turbulent, that cascades to small scales and eventually might reach solar system scales or might not. That's actually one of the questions. That can produce scattering. If that is inefficient, if scattering by the turbulent cascade to small scales is not effective, then absent that scattering, what would happen is the cosmic rays would happily try to leave at the speed of light. That turns out to be a horribly unstable situation. And there's all kinds of instabilities that the cosmic rays trying to leave at the speed of light generate. In particular, the most important of those is known as the streaming instability, which is that if the cosmic rays move through the interstellar medium faster than the local Alfvén speed, and by that I mean the average speed of the cosmic ray distribution function is larger than the Alfvén speed, there is an instability that sets in, which is basically an instability of this exact resonance that I was talking about here. And that instability grows in amplitude, back reacts on the cosmic rays, and stops them from moving on average any faster than the Alfvén speed. And what's interesting from the physics point of view is that in this picture of the streaming instability, the transport isn't really a random walk in the standard diffusive sense. Rather, the cosmic rays are just limited from moving no faster than the alphane speed. It's more like an advection or a streaming, but at a speed relative to the gas of about the alphane speed. And this difference in physics is important actually for a lot of the implications of cosmic rays for galaxy formation. And we actually don't know which of these is the right theoretical picture to describe cosmic ray transport. That's still an outstanding question. And it's one of the bigger, most interesting theoretical questions. It's one that I've been thinking about a lot and not making as much progress as I would like, to be completely honest. Just a very hard problem. I'm happy to, mostly I'm not going to talk about that work because it's a little more detailed, but I'm happy to talk about it if people have questions. Okay. I want to say a little bit first about the kind of impact of cosmic rays in lower mass galaxies, Milky Way mass and lower, where they might drive winds, affect the CGM, et cetera. And to do that, I first want to tell you how myself, Todd Thompson, other collaborators, have tried to calibrate the uncertainties of cosmic ray transport using observation. So we've tried to say, although there's a lot of theoretical uncertainties in cosmic ray transport, we can get around some of that using the observations that we have to calibrate how cosmic rays leave other galaxies, not just the Milky Way. I'm going to skip over the radio stuff in the interest of time. Happy to answer questions about that. I'll talk about the gamma ray stuff because that's actually, I think, the most important constraint. So I think the constraint that's been the most useful in constraining cosmic ray transport in other galaxies is Fermi gamma ray observations of pion decay. And the reason this is so important is that we can directly observe the GeV protons that have most of the energy in cosmic rays. So pion decay directly constrains the energy density of the cosmic rays that matter the most dynamically in galaxies. And those are the GeV particles. And in addition, it turns out that the pion decay is the dominant gamma ray emission channel for most star-forming galaxies. So this emission is also observable. So the basic reaction is a cosmic ray proton hits a neutral hydrogen atom that produces a neutral pion, which decays into a gamma ray. It also produces charged pions, which decay into neutrinos and electron-positron pairs. Those neutrinos might be detectable. Avi and Ellie Waxman did some nice work on this. That I really kicked myself for not having thought of, given that we had done the gamma ray version of the argument that they put forward. The cross sections for these reactions are known. They turn out to actually be pretty independent of energy as long as you're above the rest mass energy of the pion. And the cross section turns into a time scale for a cosmic ray proton to lose energy to pion decay, which is about 50 million years if the density of the gas is about a particle per centimeter cubed. And that time scale, you'll notice, is interestingly similar to the time scale for cosmic rays to leave the Milky Way of 30 million years at a GeV. And so that means that pion decay sort of competes with escape in terms of loss processes. So the prediction that Todd Thompson and Ellie Waxman and I made well before Fermi was launched, actually, was that Fermi would be a great probe of cosmic ray transport in galaxies, basically because if the pion decay time scale is less than the time for cosmic rays to leave the galaxy by this random walk or streaming, then most of the energy in cosmic ray protons would go into pion decay. And in that regime, there should be a linear relationship that we predicted between the GeV gamma ray luminosity of galaxies and the star formation rate of galaxies. And that linear relationship is basically just set by how much energy each gram of star formation puts into cosmic ray protons. And if it's about 10 to the 50 ergs of energy per supernovae, which we think is about right, then it turns out the normalization of this linear GV star formation correlation is about 3 times 10 to the minus 4. So Fermi has now observed this in about a dozen or more galaxies. It's a hard measurement to make, just because, compared to luminous AGN, star-forming galaxies are rather faint in the gamma rays. And the data is shown with the black points and then a few red points up here. So these include systems you know and love, like our own galaxy, the Milky Way, Andromeda, the Magellanic Clouds, M82 and NGC 253, which have been particularly important, I would argue, ARP 220, NGC 1068. The dashed line is this linear correlation that we predicted. The dotted line is kind of a best fit to the observations. And the basic takeaway is that with the possible exception of the most luminous star-forming galaxies, which have the densest interstellar medium, systems like ULERGs like ARP 220, in most star-forming galaxies, most of the cosmic ray proton energy is not lost to pion decay because we don't see it in the gamma rays. Instead, the cosmic rays have to leave the galaxy and go out into the halo and out into the circumgalactic. That's sort of the takeaway. We would love, of course, for the data to be better, to be able to bin galaxies by metallicity and surface density, not just star formation rate, but we can't do that with the present sample. And so we're sort of restricted to this correlation between gamma ray luminosity and star formation. One can turn this relatively easily into a constraint on the cosmic ray diffusion coefficient in other galaxies. It's an order of magnitude estimate that you can check after the talk, or actually while I go through this slide. It's just a few lines of algebra, that the ratio of the time for cosmic rays to random walk out of the galaxy to the pion decay time scale basically just depends on the size of the region that cosmic rays are scattering in, which is about the size of the galactic disk, to the surface density of gas, and then the cosmic ray diffusion coefficient. This A pion is just basically constants like the cross section for pion production. And interestingly, if you take the observations to invert the observations to try to constrain the cosmic ray diffusion coefficient in other galaxies, what we find is a cosmic ray diffusion coefficient that is surprisingly similar across other galaxies. It's a few times 10 to the 29 centimeters squared per second in the Magellanic Clouds, the Milky Way, M82, et cetera. And that might actually be a quite interesting constraint on cosmic ray propagation. But for now, what I want to do is use that to constrain the properties of galactic winds driven by cosmic rays. And the argument, how this constraint works, is basically as follows. There's a maximum possible mass loss rate that cosmic rays could drive from galaxies that's set by energy conservation. And the maximum mass loss rate is actually quite big. It's given by the following argument. Imagine there's a total rate at which cosmic rays are being dumped into the interstellar medium by supernovae at E dot cosmic ray. The most mass you can drive out of a galaxy by cosmic rays is then given by using all of that energy to escape the gravitational potential of the galaxy with no energy left at infinity. So basically the terminal speed of the wind is 0. So the energy you dump in goes into unbinding mass from the gravitational potential. That's the maximum mass loss rate. And that's a big number. For a galaxy, a dwarf galaxy with an escape speed of 100 kilometers a second, for the typical 10 to the 50 ergs in cosmic rays per supernovae, you get a mass loss rate which might be 10 times the star formation. That's a big number. That would be interesting from the point of view of understanding galaxy. The problem is, in this limit, this is a limit in which the cosmic rays leave the galaxy very slowly, so that at infinity you have no energy. You're just slowly lifting the gas out of the galaxy and the cosmic rays along with the gas. And in that process, the speed of the cosmic rays is at every point in space/time much less than the local escape speed of the galaxy. But if you leave the galaxy slowly, you have plenty of time to produce gamma rays by pion decay, and it turns out you vastly overpredict the gamma ray luminosity of galaxies like the Milky Way, the Magellan Clouds, M31, M82. And so we can use our constraint on the cosmic ray diffusion coefficient to constrain the mass loss rates of galaxies. And we've developed theoretical models for outflows driven by cosmic rays that depends on the diffusion coefficient, depends on the size of the galactic disk, the sound speed of gas in the galaxy that sort of gets the sound speed initially gets the outflow going. But that observational calibration is a very low mass outflow rate compared to this maximum possible value. It's a mass outflow rate that's a fraction at most of the star formation. And so the basic punchline from this observational calibration is that given that the gamma ray data tells us that cosmic rays leave galaxies relatively quickly because they don't lose most of their energy to pion decay, a corollary of that, given what we know about how pions are produced and what we know about the theory of galactic winds driven by cosmic rays, which we've developed both analytically and using numerical simulations, I think the conclusion is that actually outflows from galaxies directly driven by cosmic rays are relatively modest. So where do the cosmic rays end up? They end up in the circumgalactic medium, because that's sort of the point of this argument actually, is that cosmic rays escape galaxies rather than losing their energy to pion production or other processes. So what we've done then is we've included cosmic rays as a second fluid in numerical simulations of galaxy formation. These are a relativistic fluid. We've used this observational calibration of the diffusion coefficient to blindly assume, which is undoubtedly incorrect, but is sort of, not quite, but sort of the best that we can do right now, that cosmic rays have a time and space independent diffusion coefficient of a few times 10 to 29 centimeters squared per second. And then we've included cosmic rays sourced by core collapse supernovae and type 1a supernovae in simulations of galaxy formation. So the we has now changed. It's not Todd Thompson and Yanfei Zhang and Phil Kempsky. It's now Philip Hopkins and the FIRE collaboration, where we've done a bunch of calculations now, including cosmic rays. And this is a movie by Cameron Hummels showing you the energy density in cosmic rays as a function of time in these simulations of galaxy formation with cosmic rays. Time and redshift are shown in the lower left. You can see as time goes on, the cosmic rays are filling up the circumgalactic medium of lower mass galaxies, and then they're ultimately filling up the circumgalactic medium. And in fact, a decent amount of the energy even leaves the virial radius of the halo of the galaxy. So the dashed line here is the virial radius, and this is a simulation of the Milky Way mass galaxy. It turns out that in these calculations, the impact of cosmic rays is actually the strongest in Milky Way mass galaxies. And that's basically because Milky Way mass galaxies sit at this point where they sit at the maximum of the stellar mass to halo mass relation, and thus they sit at the maximum of the available cosmic ray energy relative to other energies in galaxy formation. And I would say one of the particularly interesting and not previously fully anticipated results that came out of this work is that cosmic rays can actually, in principle, dramatically change the structure of the circumgalactic medium of Milky Way mass galaxies. And so just to remind you, those who are not thinking about galaxy formation on a day-to-day basis, the circumgalactic medium is sort of the halo of gas that surrounding the galactic disk that is the reservoir, the fuel reservoir for ongoing star formation in galaxies. Gas accretes from CGM into the galaxy, fuels ongoing star formation, outflows drive mass back out into the CGM, driving both cosmic rays and also heavy elements out into the CGM. So I'm showing you plots here in these simulations of Milky Way mass galaxies from the FIRE collaboration, without cosmic rays, with cosmic rays, without cosmic rays, with cosmic rays. These are the same simulations showing basically the same information. One is a visual representation of the thermodynamic state of the gas, where red is sort of the hot CGM, green is intermediate temperature CGM, and white is lower temperature gas. So think of the red as sort of virialized gas, the normal virialized halo. Green is gas that's more in photoionization equilibrium with the ambient radiation field. And white is cool gas that has cooled to 10 to the 4 Kelvin and below that might ultimately be fuel for a star formation. And so what you see in the images and then in these phase diagrams, these are plots of temperature versus density, is that the phase structure of the CGM is extremely different in simulations with cosmic rays versus simulations without cosmic rays. Without cosmic rays, you have a virialized circumgalactic medium. Most of the gas in the CGM is relatively hot around the virial temperature. With cosmic rays, most of the gas is substantially cooler in photoionization equilibrium. And actually, most of the pressure in the CGM is actually in the form of cosmic rays. These are cosmic ray dominated halos rather than being, well, they're dark matter dominated halos. The baryons are cosmic ray dominated rather than being gas dominated in terms of pressure and energy density. And this has a number of observational implications. For instance, the oxygen 6 column density. So one of the probes of the thermodynamic state of the CGM of galaxies is to use lines of sight at different impact parameters relative to the size of the halo. That's on the x-axis, impact parameter relative to the size of the halo. And to look at the column density of different ions as a function of impact parameter. This has been done extremely productively with the cost spectrograph on HST and also at higher redshift by ground-based observations where the lines are redshifted into the rest frame optical by Chuck Steidel and others for Lyman break galaxies and systems like that. These are what's shown here. In the blue is a sample of star-forming local galaxies observed by COS, and in the red is a sample of elliptical galaxies observed by COS. And the sort of orangish reddish band with the median shown with the line here, and the bluish band, median shown by the blue line, are the simulations of Milky Way mass halos with cosmic rays and without for one particular ion, oxygen 6. In that case, the fact that there's more gas at a temperature of a few times 10 to the 5 Kelvin in the simulations with cosmic rays means you produce higher oxygen 6 column densities, more consistent with observations. On the other hand, just to be completely transparent, there are other observations where having this cooler CGM seems to be in tension with. So for example, in the Milky Way, there's work by Joel Bregman and colleagues using X-ray lines to constrain the hotter phase of the circumgalactic medium of the Milky Way. And that seems to suggest that there's actually a substantial amount of hot gas. And the simulations with cosmic rays, as I've described to you here, underproduce by a bit the amount of hot gas because a lot of the gas is in the lower temperature phase of the CGM. So I think the importance of this work is not that it definitively shows that the CGM of Milky mass halos are cosmic ray dominated. I don't think it shows that definitively because this still depends on uncertainties in cosmic ray transport. If we change the cosmic ray diffusion coefficient by a lot, or if the cosmic ray diffusion coefficient is different in the circumgalactic medium than it is in the interstellar medium, that could change these predictions. What I think this shows is that we really need to understand cosmic ray transport better to understand their impact on galaxy formation, and in particular, that the dominant impact of cosmic rays might actually be on the thermal structure of the CGM of Milky Way mass galaxies. And I think there's a lot more theoretical work and observational work sort of testing this type of model that's needed to understand this in more detail. Okay, so that's what I wanted to say about Milky Way mass galaxies. I'll just very briefly mention some work that we've done on higher mass systems, galaxy clusters, and then I'll end so we have time for a little bit more discussion and questions. So basically, just to remind you, there's a paradigm that's developed over the last decade or so, which is that relativistic jets from supermassive black holes are the energy source that suppresses the cooling of hot gas in massive dark matter halos. Galaxy groups, galaxy clusters, potentially even isolated elliptical galaxies in relatively massive dark matter halos. And a lot of the argument for that relies basically on two things. One is that it doesn't seem like there's quite enough feedback energy from star formation to offset radiative cooling of gas in high mass halos. The cooling rates are too strong relative to the available energy from stellar feedback. And also it comes from beautiful observational work combining, for instance, Chandra and the VLA observations of galaxy groups and clusters, where there's clear evidence for radio jets interacting with the hot intra-group and intra-cluster medium, the radio emitting plasma, which is synchrotron emission from relativistic electrons, seems to displace the hot X-ray emitting gas shown here in kind of a grayscale surface brightness map. And so it looks like the jets are displacing the hot gas, pushing it around, and dumping the feedback energy from the black hole into the intracluster medium. There's enough energy, at least at the order of magnitude level, coming out in relativistic jets to substantially impact the thermal structure of the hot gas in groups and clusters. But what we don't understand well, and I would say this is still a big question of how exactly does the black hole energy get transmitted relatively spherically out into the surrounding intragroup or intracluster medium. because it's not enough to just heat gas along the jet, right? You want to stop the gas over here in the group and cluster from cooling as well. You don't just want to stop the gas heat. So there's a need to redistribute the jet energy relatively spherically and relatively uniformly in time. And there's a variety of different ways that people have thought of to do this. One is waves, that time variable jets can drive waves and turbulence into the intercluster medium, and that can heat the surrounding plasma. And that's actually what I'm showing you in this simulation that we did, where a time-dependent jet is driving sort of large amplitude sound waves or weak shocks relatively more spherically than the jet itself into the surrounding medium. And the other idea is actually that most of the energy in jets, after all, is in relativistic particles. That's what a jet is. It's a beam of relativistic particles, a la Rees and Blanford. And so it's basically cosmic rays. And so if those cosmic rays can transmit their energy to the surrounding medium, maybe they're the vector by which the feedback energy gets transmitted to the surrounding medium, stifling cooling. And what we've shown in work that I particularly like over the last couple of years, and this is work led by Philip Kempsky, and when I say led, this is really his ideas as well as his calculations. What he's shown actually is, I think, an amazing result. It's that in galaxy cluster plasmas, both sound waves and internal gravity waves, which are two of the three basic linear waves in the problem, the other being the Alfvén wave, both sound waves and internal gravity waves are linearly unstable due to the presence of cosmic rays in the intracluster intragroup medium. And what allows the instability to operate, it turns out, is that the Alfvén wave, which affects how cosmic rays move through the plasma, depends on the mean free path of the hot intracluster plasma. This is basically viscosity changes the Alfvén speed in the intercluster medium conditions, and that drives sound waves and internal gravity waves linearly unstable. The sound waves, Philip has calculated, grow in amplitude until they steepen into weak shocks, shown in this numerical simulation that he's done, again, treating the cosmic rays as a relativistic fluid. The weak shocks that are produced in Philip's simulations actually bear a lot of resemblance to the weak shocks that have been seen by carefully looking for surface brightness fluctuations in the Perseus cluster. This is work that Andy Fabian is famous for. So you're seeing a hundreds of kiloparsec image of Perseus, subtracting off the mean surface brightness profile and just looking at the fluctuations due to what are either waves or weak shocks of some kind. So the speculation that we're proposing and trying to study in more detail is that cosmic rays generated in jets, in bubbles, in particular, you create these cosmic ray dominated plasmas that are very unstable to the instabilities that Philip has discovered. Those instabilities sap a lot of the cosmic ray energy in the form of waves, which can travel spherically out into the intracluster medium, depositing their energy over relatively long distances and strongly affecting the thermal evolution of the cluster plasma. And so we're kind of have understood the linear instabilities in their saturation and are trying to work out now how this actually operates in sort of a global intracluster medium context. Okay, so I'll stop there. Hope I've given you a bit of a feel for some of the interesting physics and astrophysics of cosmic rays and galaxy formation, what some of the impacts might be, why that is not pinned down yet theoretically or observationally, and what some of the interesting avenues for continued research are. So thanks a lot for your time.
Thank you.
Questions.
I have a couple questions coming in, and just a reminder to folks, if you want to message me the just sort of basic topic of your question, I'll call on you. So first we had a question from Avi. Would you like to go ahead?
Sure. Nice to see you, Eliot, and excellent talk. And it's too bad that you cannot visit us in person, given that you're much closer than in the past. So in the context of the mass carried by the wind driven by cosmic rays, I had the following question. Massive stars have winds, very powerful winds, and the optical depth to the radiation within the wind is of order unity. And what people find is that the mass loss rate of the wind is roughly given by momentum conservation. In other words, if you take the luminosity of the star divided by the speed of light, that's the momentum per unit time deposited in the wind, and that's roughly m dot times the escape from the star. So a very good fit to the mass loss rate in massive stars is given by this balance of momentum, not energy. And the difference from the energy equation that you mentioned, which gives the maximum mass loss rate, is a factor of V over C, V escape over C. Now, the question is whether that gives a closer fit to the line that you showed us, or is it still off? And I guess it could be off because perhaps the optical depth is not of order unity for that. So can you elaborate?
Yeah, so that's a great question, and you're absolutely right. There's a lot of analogies between galactic winds driven by cosmic rays, especially in the diffusion approximation, and winds from massive stars driven by radiation when things are optically thick, driven by diffusive radiation. So the analogy is a bit more to what are called continuum-driven radiation winds rather than line-driven winds. But that's exactly right. There's a very close analogy. So the momentum conservation argument definitely is closer to the result that one gets calibrating to the sort of empirically constrained diffusion coefficients. It's not exactly the same, but it is definitely much closer. So if you made an ansatz that the momentum, terminal momentum flux in the wind is related to how much momentum is being dumped into the surrounding medium, that is definitely closer to what one gets from the more detailed wind calculations calibrated empirically in the way that I described. It's not exactly the same, but it's closer. Yep, so good question.
Thank you.
We have a few questions about how the CGM is affected by cosmic rays. So Ramesh, why don't you lead the way?
So Eliot, great talk, but I missed one small point. You must have mentioned it, but I don't know, I must have blinked. You say that the CGM becomes cooler when you include the cosmic ray contribution. It kind of goes against my intuition. Why exactly does it get cooler if you add this extra pressure?
Yes, so no, that's a great question. And we've definitely, looked into that mechanistically, because I agree, it's not entirely, it's a bit counterintuitive. I think the basic thing that's going on is that in the case without cosmic rays, a lot of the gas that's actually driven out of the galaxy is driven out in the hot phase. You get a strong virial shock coming into the galaxy, so you have hot gas coming from both directions. Two things happen with the cosmic rays. One is that you actually suppress the virial shock. the cosmic rays get driven actually sufficiently far out into the CGM that they go out into the intergalactic medium and they suppress the normal virial shock that heats gas up and creates this virialized halo. And the other thing is that actually a lot of the gas driven out of the galaxy into the circumgalactic medium is initially driven out in cooler phases in the first place. So I think it's a combination of both of those things. One is that you're actually accreting cooler gas because you're suppressing the importance of the virial shock, and you're driving cooler gas out into the CGM in the first place.
Thank you.
Anna, do you want to continue along those?
Oh, yeah. Hi, Eliot. Yeah, I had a couple questions. Well, the first was regarding what you spoke about a lot of the cosmic rays leaving. Laura Lopez had a paper on the SNC a couple of years ago, looking at the Fermi gamma ray emission observations, and then also comparing it with the polarization, previous polarization. And she found that basically, if you look at the polarization, you do see the cosmic rays weaker gamma ray emission along the magnetic field lines. I don't know if you guys have looked at that with the escape fractions in your simulations to see how it follows the magnetic field lines.
Yeah, we have not done that in detail yet. And there are various, yeah, we have not done that in detail.
Yeah. Yeah, I was curious too, because I know your plot showed up to the LMC, so I'd be curious to see how that works down to the SMC and other things. Including for the diffusion coefficient. And then another question I had was, so a project that I've been working on is to try to understand the gamma ray emission in galaxy clusters, and it's a lot weaker than you would expect. And so we developed this model to kind of, we have different sources of gamma rays, so like including the supermassive black hole at the center for the BCG, and then we included like another couple of mechanisms. But with that, we can constrain either the efficiency, like how much of whatever energy goes into accelerating cosmic rays, or we can also look at the diffusion coefficient. So either based on that. So I'm just curious. So like with our model, we find that you'd expect the most energy injection would likely be due to the CGM, supermassive black hole. Sorry, it's not CGM, BCG, supermassive black hole, because that's the most massive. But now I'm curious, but then we have to have a much lower diffusion coefficient because the escape fraction needs to be high to account for the low gamma ray emission, or we need a very low efficiency, or now with what you talked about, the fact that you're transferring energy to drive these alpha waves. So how much of that energy would you say is doing that?
Right. So just maybe to step back for everybody else, and then I'll answer you.
Oh, sorry.
No. I think this is a great set of questions. So I could have talked about trying to observationally calibrate cosmic ray transport, as Anna's nice questions alluded to. I could have talked about that in the context of galaxy clusters just as well as galaxies.
Yeah.
The difference is that in galaxy clusters, we have not yet detected the gamma ray emission from pion decay. This was a big hope with Fermi, actually, is that it would detect it maybe in
very
Virgo.
minimal.
Yeah. But it's not as well characterized, even though these star-forming galaxies are only moderately well characterized. It's yet less well characterized in galaxy clusters. And so, as Anna said, this is a constraint on some combination of diffusion coefficient, efficiency of injecting cosmic ray energy. I think the direct empirical constraint is that the energy density in cosmic rays is not equal to the thermal energy density of galaxy cluster
like
plasmas,
1%.
like it is roughly in the Milky Way. Instead, it's 10% of that or 3% of that, or probably depends exactly where you are in the cluster and whose model you take. Those are the typical numbers. So I think that's interesting for two reasons. I mean, one is it really constrains the direct heating
Mhm.
of cosmic rays, direct heating of the thermal gas by streaming cosmic rays,
Mhm.
which is one mechanism that people have invoked to heat the intracluster medium. And actually the specific reason that when I talked about the instabilities generating waves and them traveling out, I sort of intentionally said that maybe the waves are excited near the bubbles and then they travel out. And the
Mhm.
reason I framed it that way is precisely because I think the cosmic ray energy density, it sort of has to be high near the bubbles because they're
Yeah.
relativistically dominated plasmas. But for just the observational reasons you gave, it seems to be low elsewhere.
Yeah.
So I think the region that is the most efficient at generating the waves is in fact the plasma sort of at the boundary between the bubbles and the rest of the intracluster media, because that's where the cosmic ray energy densities are the highest.
Yeah.
Okay, and I think the question that we're trying to answer now, which is still a bit challenging, is how far the waves get and propagate to transport their energy. Well, that depends on the wavelengths of the waves that are excited and how quickly they steepen. And so that depends, not just on the linear instability, but on how it saturates nonlinearly. And so that's the part of the problem that we're still trying to understand. But I think for the reasons that you gave, I think either direct heating of the intracluster medium by cosmic rays or cosmic rays exciting in situ waves, 100 kpc away from the jet, I think that's probably unlikely.
Okay.
Because the cosmic ray energy densities seem to be pretty low as constrained by the gamma ray data. That's my guess, but this is something that we're also, trying to think through and make sure we understand exactly what the observational constraints are, et cetera.
Yeah, sorry, I haven't looked at this project in a while, so I've been finishing up and doing lots of other things, but something I've been meaning to get back to working on and finishing. But yeah, I'll send you an email. I'll talk to you more about it.
Okay. Yeah, no, that's great. Thank you.
Yeah, thanks.
Thank you so much. I think we're reaching our 12 o'clock threshold there. So maybe we can join in thanking Eliot one more time. There are a few questions left. I don't know if you can stay for 5 more minutes, Eliot.
Yeah, I'm happy to.
But people who need to leave, go ahead. But if you had an outstanding question, feel free to stay if you're able to.